Welcome to this explainer. Today, we're diving into a pretty fascinating mystery, the cleanroom ghost that haunts sterile pharmaceutical manufacturing. We're going to unpack a massive visibility problem in one of the most highly regulated industries on Earth, and we'll explore how cutting-edge technology is entirely transforming contamination investigations. We're talking about moving from a reactive sample and culture guessing game into a highly predictive, physics-based discipline. Now, it sounds like pure science fiction, but seriously, what do you do when the world's most sterile room is, well, haunted? That is the literal multi-million-dollar question facilities face when some microscopic culprit survives harsh chemical wipe-downs and completely ruins product batches. We aren't talking about a random, isolated event here. We're talking about microbiological data deviations that reappear in the exact same location, the same room, or the same product stream, despite repeated remediation. It's this persistent reservoir that's just completely invisible to routine environmental monitoring.
So, here's our roadmap for solving this case. We'll start with the cleanroom ghost phenomenon itself, then dig into the root causes of persistent contamination. After that, we'll unpack the digital twin solution, look at how we hunt with virtual simulation, navigate the regulatory compliance rules, and finally, wrap up with adoption, outcomes, and limitations.
Okay, part one, the cleanroom ghost phenomenon. Let's define exactly what it is we're actually hunting in these highly controlled environments.
While the real culprit behind these recurring microbial deviations is often something called a biofilm. Think of it as an invisible fortress that static sampling simply misses. Once these organisms embed themselves into a self-produced protective matrix, maybe on a gasket, a drain, or deep inside ductwork, their resistance to antimicrobial agents absolutely skyrockets compared to normal free-floating cells. They literally just wait out the standard disinfectant contact times and then continually repopulate the surface. That's what produces that incredibly frustrating intermittent recurrence that gives our ghost its name.
And just to give you a sense of what we're up against here, some of these environmental organisms actually carry incredible DNA repair genes and spore-forming capabilities. They are so ridiculously tough that cleanroom microbiology research literally crosses over with NASA's planetary protection studies. We are dealing with phenomenal biological survivors here, exhibiting some straight-up alien-like survival skills.
Moving on to part two, root causes of persistent contamination. So why do traditional investigation methods just keep hitting dead ends? Why do we keep failing to see what's right in front of us?
You see, old-school detective work relies on static snapshots, and those just can't capture the complex, three-dimensional airflow dead zones or the thermal gradients where these problems hide. Traditional root cause frameworks often just default to blaming humans, because let's face it, we're the easiest target statistically. And yeah, while personnel shedding skin is a huge factor, over-attributing events to human error can completely mask the real underlying issues. Routine air change calculations don't reveal unintended recirculation paths or stagnant air pockets created by localized heat sources. Plus, traditional culture-based sampling takes 24 to 72 hours for colonies to grow, which severely delays detection. To give you a specific case in point, there was one facility that spent immense resources before finally finding a gram-negative bacteria lurking in dryer condensate. These bacteria are notorious for their tough, protective outer membranes, and this colony was way outside the routine sampling grid. The facility looked at the cleanroom air, purified water, raw materials, everything within their normal protocols. But the reservoir was ultimately found hidden deep inside hard-to-inspect pipework. It really goes to show that if your sampling grid isn't looking in the exact right physical location, the ghost is just going to keep haunting you.
Which brings us to section 3, the digital twin solution. Let's look at how we actually shine a light into every invisible corner of a facility.
We can now hunt these ghosts using a digital twin. This means moving away from a reactive culture swabbing exercise into a predictive, physics-based discipline. Now, a digital twin isn't just some basic 3D CAD model, right? It's an active, continuously running virtual replica. It bidirectionally communicates with the physical environment so that it's always perfectly synchronized with real-world conditions. And these 4 core components are what work together to render that invisible, turbulent airflow entirely visible. First, you've got a computational fluid dynamics, or CFD, engine solving really complex transport equations. Then, you layer in thermal mapping. This is vital because heat from equipment, lighting, and humans creates little convective micro-recirculation zones that totally disrupt unidirectional airflow. Next, you integrate continuous data from IoT sensors, particle counters, and temperature probes to feed the model. And finally, predictive machine learning analyzes all that historical data to actually anticipate excursions before they even happen. It's pretty amazing. Section 4. Hunting with virtual simulation.
Let's see how we actually apply this tech out in the real world to catch the ghost.
When you compare reactive sampling with predictive digital twin modeling, it's honestly like upgrading from a static photograph to a continuous 4K video camera for your investigations. In the traditional reactive approach, you wait days for cultures to grow, check a few fixed points, and typically just blame a worker's gowning technique. But with a predictive digital twin, you're leveraging near-continuous detection. You can actually see the entire 3D airflow field across the volume of the room, which lets you trace plausible airborne pathways right back to their source using pure physics.
So if a ghost does appear, here is your 5-step workflow to track down those hidden vectors and test solutions virtually. First, reconstruct the historical operating envelope, logs, records, all of it. Second, run the twin against those specific conditions to find thermal anomalies or stagnation zones. Third, cross-reference those flagged virtual locations against the physical space, prioritizing things like drains and gaskets. Fourth, use rapid microbial methods, which give you results in hours instead of days to verify the microbe's presence. And fifth, simulate your fix, like maybe moving a diffuser. You test it in the virtual model to ensure it actually works before paying for costly late-stage physical rework.
All right, Section 5. Navigating regulatory compliance rules. Because, of course, any futuristic tech has to be grounded in present-day reality and very strict pharmaceutical rulebooks. You can't just deploy unproven software into a highly regulated GMP environment.
Global regulators like the EU and the FDA absolutely demand a rigorous risk-based contamination control strategy, or CCS, for any facility. EU GMP Annex 1 mandates this directly, requiring facilities to merge quality risk management, facility design, and monitoring into one single framework. The FDA's 21 CFR and various ISO cleanroom standards demand a very similar level of integrated control. And digital twins actually perfectly support the later phases of this CCS maturity model. They enable predictive trends instead of just checking a box for baseline monitoring. In phase 1, you're really just developing your strategy. But as you mature into phase 2 with data analytics, and phase 3 with full integration for continuous, near-zero defect improvement, digital twins become incredibly powerful. Regulators are increasingly supportive of this kind of model-based evidence, assuming it's appropriately validated, of course. Moving from phase 1 to phase 3 means you aren't just reacting to problems anymore, you're literally engineering them out of existence.
Finally, Section 6. Adoption, outcomes, and limitations. Let's do a quick reality check on where the industry actually stands today, because the outcomes are undeniably impressive. One global manufacturer even reported a 20% reduction in contamination incidents after implementing IoT-enabled continuous monitoring.
But despite this being a projected $8.5 billion market by 2032, only about 31% of manufacturers plan to adopt this in the next 2 to 3 years. That leaves a massive 69% of manufacturers delaying adoption. So why is that? If it catches ghosts and saves millions in ruined batches, what's holding everybody back?
Well, integrating virtual versions of proprietary processes creates massive cybersecurity concerns. You're literally encoding your facility layouts, product parameters, and process knowledge into a connected network, and that makes companies absolutely terrified of exposing their IP. On top of that, there are huge prerequisites for data infrastructure. You need high-end systems to run CFD at useful refresh rates, plus you face strict GMP validation hurdles. But perhaps most importantly, you need organizational readiness. If your workforce can't effectively interpret these predictive models to drive real operational improvement, the technology is essentially useless.
Ultimately, it comes down to this. Digital twin simulation is a complementary predictive layer that narrows the search space. It works alongside, not instead of, rapid microbial methods and real-world swabbing. A digital twin is a hypothesis generation tool. It tells you exactly where to look, but you still have to go look, right? It doesn't replace your documented contamination control strategy. It dramatically enhances it by giving your team X-ray vision into the room's invisible physics. So I'm going to leave you with this final thought to consider about the invisible risks lurking in your own facilities. In an industry where a single microscopic ghost can entirely halt production, can your facility really afford to keep relying on what it can't see? It's a pretty compelling question for any sterile manufacturer navigating the future of quality control. Thanks for joining me for this explainer, and I hope it cleared the air on how digital twins are changing the game.